All right. Okay, so when we look at these figures, the first one, the sub-panel here of C, is telling us the change in global average upper ocean heat content. So it's a measurement of how much heat is in our upper portion of the ocean. And you don't see it here because I cropped these figures just for this purpose, but each one of these different colors here is a different measurement technique. So we can see that the 5 or 6 different colors here, different ways of measuring the heat content, all show an increasing trend, upward rise in the amount of heat in the oceans. Okay, so, and this is in 10 to the 22 joules, so a lot of heat. The bottom panel is showing the global average sea level change, starting pretty much at 0 up to about 200 millimeters. And we can see that as we move forward from the 1900s to this goes to about 2010, we see that the global average sea level has increased by about 150 millimeters. Okay, great responses, great discussions in the chat here. And so from this data, we can actually calculate things like rate of change, right? So for example, how much is the ocean sea level changing on average through a certain period of time? And then we can project out what the sea level change could be in the future based on that rate of change, right? For example, how many millimeters per year? What's the slope of our line? And then we could say, okay, by 2050, using that slope, we will know or we'll have an estimate of what the sea level change would be. Okay, and so that's what we do a lot of times when we're thinking about forecasts or projections into the future. We have to use the data that we have, and we do the trend lines like you are doing in your homework. And we can also look at, maybe the trend isn't the same. Maybe the rate of change is not the same throughout the whole record. And so we have to figure out what is the best piece of the record that we should use to forecast the future or project the future. All right, so today we're going to be talking about our ocean, which is why I chose to talk about some of our ocean. So let's think about our atmospheric moisture. So we talked on Tuesday a lot about atmospheric moisture. So I have just a recall poll here. There's 4 questions based on our one sample here. So take a few moments, answer our 4 questions about this sample of air. All right, 20 more seconds. All right, here we go. So different ways of looking at how much moisture, how much water is in our air. Okay, so when we read this graph, what is the air temperature of the parcel? Well, there's two axes. We have temperature on the X and water vapor content on the vertical or Y. And so when we're reading the temperature, we're just going to go straight down and our temperature is 30 degrees C. Great. And what's the moisture content? How much moisture is in that sample? Or maybe we consider it the actual vapor content. And that's going to be reading over to the left here. So the actual vapor content is about 15 grams per kilogram. Okay, so there's 15 grams of water per kilogram air. And let me, oops, didn't mean to do that. That's okay. You can click in on the other questions today. Okay, so sorry, I lost my markers here. So it's 30 and 15 grams per kilogram. For dew point, we are just going to decrease the temperature. Okay, so decrease the temperature, keeping the vapor content constant. Where we cross the saturation mixing ratio line is dew point. And then we have to just read down. So I put about 20 just because we're close to that intersection. It's more like 21-ish, but the answer here is about 20 degrees C. And then relative humidity. Relative humidity is a ratio between how much vapor is in the air and how much vapor is in the air at saturation. Okay, I also told you it's like walking along the line here on the same temperature. How close are we to the blue line? Okay, so the actual equation would be 15 grams per kilogram over how much vapor we need at that temperature for saturation to occur, which in this case is 25 grams per kilogram. That whole thing multiplied by 100%. And in this case, it is 60%. Okay. Again, you can imagine you're walking along that line. We're about 60% of the way to that saturation line. And so relative humidity is a really great indicator of how dry the air is. Lower relative humidities mean the air is much further away from that saturation line. We feel relative humidity. Like when it's very dry, when we have Santa Anas, it's dry. Like your skin gets dry. For me, when I lived in California, Santa Anas, I would have really dry lips. My skin would get dry on my fingernails, my cuticles, right? So why? It's because all of the moisture from my skin is getting taken up. It's getting evaporated by the dry air. Okay, because dry air is thirsty air. Okay, and then we talked about adiabatic heating and cooling, the idea that we can change the temperature of air without removing or adding heat, simply by changing the pressure that is exerted on that air. And we can do that by moving air up or down in the atmosphere because pressure, atmospheric pressure, is a function of height or altitude. As we move higher in the atmosphere, atmospheric pressure decreases because there's less air above our heads. That air is being pulled to the Earth's surface by gravity. So we have more atmospheric pressure near Earth's surface, near sea level. So when we push air up, it will cool by either the dry adiabatic lapse rate, if it's not yet at saturation, or it will cool at the moist or wet adiabatic lapse rate if it's saturated. Okay, and that can determine where in the atmosphere we will form clouds. Are we going to form them low or higher? All right, and then we talked about residence time, and we will talk a lot more about residence time next week, or in 2 weeks when we really get into the carbon cycle. Where is carbon stored on our planet? But remember, residence time, you have to know the size of the reservoir, in this case, the lake, and you have to also first determine that the system is in steady state, meaning that the size or the flows, fluxes in, sources in, is equal in value to the sinks out. If they are not in steady state, you cannot actually calculate residence time. So you have to be in steady state. So in this case, we're in steady state, river inflow and evaporation. They equal the same total value. And then we would divide 12 by 1.5 to find the flux, or excuse me, the residence time. Now, for reference, when we think about residence time of gases in our atmosphere, the residence time is very different for the different gases. So for example, hours, days, we have compounds like nitrogen dioxide, nitrogen oxide, sulfur dioxide, water vapor, H2O, has a very short residence time because it's evaporating and condensing, forming clouds, maybe even precipitation. It is constantly being moved around the different reservoirs. Longer lived compounds like tropospheric ozone has a residence time of weeks or months, and our very, very long-lived compounds have long residence times. For example, CO2 in the atmosphere, it's about 1,000 years. Methane is about 10 years. We have our CFCs, our chlorofluorocarbons, which we'll get to at the end of this class, but those are about 100 years. Okay, so different gases, different compounds in our atmosphere have different residence times. So when we think about that, it matters in terms of how we can change climate, right? Just because we stop emitting carbon dioxide today, because it lives or has a residence time of such a long time, we may not see the change in the reservoir for some time. But that doesn't mean us stopping emissions isn't benefiting the climate. Okay, so we're going to talk more about residence time towards the end when we talk about full-blown climate change. Okay, so today we'll talk about how the oceans and atmosphere interact and our ocean circulations, and we'll talk about El Nino, which is very front and center because we are in a El Nino phase of the El Nino Southern Oscillation. What does that mean? Talk about it. Okay, so as mentioned, our ocean, just like our atmosphere, is moving heat from the equator to the poles, and then the lack of heat from the poles to the equator. Okay, so we're moving hot stuff north or south, depending on which hemisphere you're in, and that cold stuff back to the equator. And what's important is that the atmosphere actually has a tremendous impact on our surface oceans. Our atmosphere and our oceans are constantly interacting, exchanging materials, moisture, and also our atmosphere is going to help drive and move some of that surface ocean water. And our oceans are really, really important for transferring and storing heat. We saw that in our warm-up. They store a lot of that heat because water doesn't change its temperature super quickly, right? That high specific heat, it can store a lot of heat without changing its temperature that much. And so our oceans are a big reservoir of heat, and they're also a really big reservoir of carbon, which can regulate our climate. So just like our atmosphere, our oceans are always in motion. Like I mentioned, redistributing that heat from the equator to the poles and vice versa. Now, just like our atmosphere, where we have surface circulation and then high up circulation, we have similar separations in our ocean. We have surface circulation, basically how the surface ocean is going to move above about 400 kilometers depth. And that 0 to 400 meters, I said kilometers, 400 meters depth is driven by atmospheric winds. And then below that, below the 400-meter depth in the ocean, the rest of that water is driven by density. Okay, so when we look at our upper ocean circulation, we can see that there's a lot going on. Okay, we see that there are some interesting circulations and interesting patterns. And so what is driving that? Why do we get these circulations in our surface oceans? The main reason for that is the wind, that blowing air, as it's blowing across the ocean surface, it's dragging and pulling the water with it. And because the ocean water is not technically connected to the earth, it is on the earth's surface, but it's not tied down to the earth. It's going to experience Coriolis effect, that deflection because of Earth spinning. Okay, and what we get is what we call this Ekman spiral. If you look down on the water column, it looks like the currents at each depth in the ocean are spiraling. And it has to do with the Coriolis effect, right? So if your winds, shown here in the yellow, are dragging on that direction, the surface current is going to be a little bit off, about 45-ish degrees off from that wind because of the Coriolis effect. Now, when we're trying to calculate average flow, like what is the most of the water in that upper 400 meters doing, we call that Ekman transport. It's the average flow of the water, and it is 90 degrees to the right or left of the surface wind if you're in the northern southern hemisphere, right? We know that in the northern hemisphere, the Coriolis is 90 degrees to the right of flow, and in the southern hemisphere, it's 90 degrees to the left of flow. Okay? And so here in my example, I have the wind blowing with that yellow arrow on top, and then my Ekman transport, the net water movement, is 90 degrees to the wind direction. So based on this example here, would this diagram be showing what's happening in our northern hemisphere ocean or our southern hemisphere ocean? Alrighty. So northern hemisphere, 90 degrees to the right, that Coriolis effect. And so if we look at our diagram here, the wind blowing that yellow arrow, and then we're 90 degrees to the right, okay, is our net water. So this is a northern hemispheric diagram. Okay? Now let's practice again. Here I'm showing you the direction of the wind. What would the direction of the ocean current be in the southern hemisphere? All right, that's okay. There are like 20 more questions today. Okay, so here we go. We're in the southern hemisphere. If this is the direction, these arrows, of our wind, then in the southern hemisphere, our water will be deflected to the left and to the left. Okay, so north, our ocean current would flow to the north. Great. Now, unlike our atmosphere, which is not impacted nearly as much by land, right? Our atmosphere, especially high up in the jet stream, doesn't care that there's land 5,000 meters below it. our ocean currents are going to be interrupted by our continents. And so what happens is that we get vertical movement of water. And we are going to call that upwelling, where water is coming upward, and we're going to call it downwelling, where water is moving down. And so what happens in upwelling is that if our wind direction, in this case, we're in the northern hemisphere, if our wind direction is shown here with the arrow, then our Ekman transport, the surface current is moving away from the coastline or the shoreline. And so what's happening is, again, we can't just have a void, right? We can't just move water away and then there be nothing there. And so what happens is as the water is moving away from the shoreline, water from beneath or deeper is coming up at the coastline to kind of fill in the water that was leaving because of the surface ocean current. The opposite is true with downwelling, where if your wind direction leads to a surface current, surface ocean current, that is pushing onto the shore, well, that water is not just going to flow inland. That's just not how it works. There's not enough power for that. What's going to happen is that water will start to sink down. And so that's downwelling. So if the water is coming up from deeper, upwelling. If it's sinking down, downwelling. Now, the difference between those is actually really, really important for the nutrient circulation of our ocean. So deeper water, water that's coming from down deeper in our oceans, has had time to replenish the nutrients. Okay, so we're going to talk about the ocean carbon cycle and the ocean biological pump, but there's a lot of productivity in our oceans. We have the phytoplankton, the little tiny plants that are harvesting carbon dioxide from the ocean water and growing, right? And producing oxygen. They produce a whole lot of oxygen. And then things eat that phytoplankton, like zooplankton, little microscopic critters. And then that's our food chain, right? Things eat the zooplankton, then you get krill, you get fish, you get higher orders in our food web. And then all of that stuff, all of that living stuff, when it dies, it sinks to the bottom of the ocean. And we have decomposers and respiration processes that can take that nutrients, all those nutrients, and then they can come back to the surface. And the way that is happening is through upwelling. So that deeper, colder, and nutrient-rich water is getting pushed up to the surface where that phytoplankton is going to thrive because it has everything it needs there. It's going to have the sunlight, it's going to have the CO2, carbon dioxide, and then it's going to have the nutrients it needs for its processes. Okay, so when you have ocean upwelling, typically you have very productive oceans. Well, the opposite is true for downwelling. Okay, so when you have warmer ocean, warmer surface waters getting pushed down, these are nutrient poor because the phytoplankton, all of the things living on the surface in our oceans are really taking up all the nutrients. And nutrients are usually the limiting factor for ocean life. I mean, it's for us too, right? Like we have to eat to get our nutrients. We need that resource, and it's not an unlimited resource. And it's not an unlimited supply in our surface oceans. And so areas that have ocean downwelling are not biologically productive. Okay, this is not where you'd want to go start a new fishery, right? Where you're looking for different fish species because you're not going to find it really there because it's just not a significant food chain because we're missing the nutrients. So here's North America, and this is real, this predominant wind direction off the coast of California. So what's happening? We're going to have upwelling or downwelling off of California. All right, here we go. So, well, the first thing we have to ask ourselves is, well, what hemisphere is California in? Well, it's northern hemisphere, which means Coriolis is going to act to the right of the wind direction. Again, now this one, sometimes you just have to turn your head upside down and think about where the wind is flowing. So the wind is flowing from north to south, deflected to the right. So our ocean current in yellow is moving away from the shore, which means we're going to have deeper ocean water upwelling to fill in that. Okay, so if this was a cross-sectional diagram, we're going to have our surface waters moving away and our deeper waters moving up, which means it's very productive. That's why you can go to the beach and see dolphins and seals and all of those higher order animals because there's so much life, right? Those dolphins and those seals need the fish and all of their food supply, and you're only going to get that if there's enough nutrients. And so that upwelled water along the coast of California is colder, saltier, and contains a lot more nutrients. And this is another reason why the coast of California is a bit colder than other coasts, okay? Because we're getting some colder water coming up. So that phytoplankton, as I mentioned, they're basically microscopic marine algae, very tiny little plants. What's really cool about modern technology is that we can use satellites to look at the chlorophyll signal, right? So these plants, they contain chlorophyll, that green pigment, um, and we can use our satellites to just focus in on that wavelength. We can see all these really cool phytoplankton blooms in our ocean. Now, phytoplankton play a very significant, critical role in climate because they are taking up large amounts of CO2, carbon dioxide, and then in return giving our atmosphere a lot of oxygen. In fact, the estimate is that over 50%, maybe even more like 70, 75% of the oxygen we breathe is due to phytoplankton, not the land trees. Okay, so these phytoplankton are doing some serious work. Now, this is what I mean by looking at these phytoplankton blooms. So this is a satellite image off the coast of New Zealand, and we can see the swirly, cool pattern here. This is a bloom of phytoplankton in the spring when sunlight kind of comes back and they go into high gear, taking up CO2. And yeah, it's pretty remarkable. We'll talk more about phytoplankton in a few weeks. Okay, so these maps here are showing sea surface temperature on the top, so we can see that the redder orange colors, it's where our oceans are warmer. Makes sense. Our oceans are generally warmer in the tropics and much cooler in the poles. And then the bottom is showing the phytoplankton chlorophyll concentrations, again, based on satellites. And so we can see all of these areas circled are areas of higher chlorophyll. And these are really productive ocean waters. So we can see the coast of California, C1 over here, very productive. Our equator, our Pacific Ocean, heavily a very strong productivity region, and our Southern Ocean, actually off and around Antarctica, lots of algae down there, a lot of phytoplankton. Okay, so now when we look at our surface ocean circulation, okay, so these are the big ocean currents on our planet. Do you notice any trends in our currents? In particular, pay attention to the colors here because the red is showing warm ocean currents and then the blue is showing cold. Do you see any trends in our circulation? All right. Great one. So some warmer currents in the north, we have it's circular. Okay, yeah. So you picked up on that there's some sort of circular pattern to these rotations, to these circulations. Great. And we also have warmer currents are coming from or around the equator. Okay, yeah. So we have our red equatorial warm currents. And then we also have these currents that are moving warm water from the equator up to the north or to the poles. We could also see that in the south, right? So the East Australia current moving from the equator to Antarctica. And I was just talking about Finding Nemo yesterday, and the turtles are like, yeah, dude, get on the EAC. Well, the East Australian current is right there. Okay. I don't know. I might have dated myself, but one of my all-time favorite movies, Finding Nemo. It's just really cool. Lots of science in there. Okay. So what's happening here is we have the vertical movement, that upwelling or downwelling, but we also have rotation. Okay. And that circulation is what we call a gyre. They're kind of like high pressure systems in our atmosphere, but they're higher water levels caused by water flow. Okay, so what are you talking about? Okay, so let's think about our three-cell model here for a second. Recall our three-cell model. At the equator, what direction are our surface winds flowing at the equator or blowing at the equator? All right. So at the equator, if we remember, we get what we call easterly winds or those trade winds at the equator, where we have most of the flow is coming, whoops, is coming from the east to the west. Those are the trade winds, right? The reason they're called trade winds is way back in the days where we had explorers on sailboats, they would get into the trade winds to be able to go from Europe to the Americas. Okay. So we have winds blowing from the east to the west at the equator. Now, how are our winds blowing at the mid latitude, say more around 30 to 40 degrees north? Alrighty. So they are flowing the opposite direction, right? So our westerly winds are blowing this direction here. So we can see that we actually get this rotation in our atmospheric winds, which are going to impact our ocean. Okay, so here's what's happening. I'm going to draw this out for you so you can visualize the actual effect. So at the equator, our winds are blowing mostly from east to west, easterlies. Okay, now what's that going to do to our ocean water? Where remember, our ocean water is going to be deflected. Ekman transport will be to the right. Okay, so the black color here is going to be our ocean currents. Now, if we go back to our mid latitudes, our atmosphere, which is shown in red, is blowing from the west to the east, and that's going to lead to the ocean current moving down to the south, to the right of flow. And what we see here is that the ocean currents are coming together. Okay, they're converging. And what that actually is doing is it's pushing ocean water together at the surface, kind of like piling the water up a little bit. Now, you can't really pile water, right? You try to push water together, it's going to flow outward. And it does. And the thing about that is it's going to flow from higher heights to lower heights, just like air. And it's going to flow with that Coriolis effect, right? So it wants to go from high to low, it gets turned. It wants to go from high to low, it gets turned. And so what we get is a big circulation. Let me do a different color. Let's do purple, where the overall movement is in this circle, or in this case, it's a clockwise flow. And these are our ocean gyres, okay? So one of you noticed that they're circular, right? And so our North Pacific gyre rotates clockwise, our North Atlantic gyre rotates clockwise, and our Southern Hemisphere gyres are rotating the opposite direction because the Coriolis effect is in the opposite direction. Okay, so 5 major gyres, 2 in each of our Pacific and Atlantic basins, and then 1 in the Indian Ocean. Now, these are the surface ocean moving a lot of heat. And because of that, we get, differences in climate on our ocean basins, because one side of our ocean basin is moving a lot of heat to the poles, and then the other side is moving a lot of cold water from the poles down to the equator. And California is located on the side of the ocean basin that's colder. And that's why the climate of California is a little bit more desirable for people because it's not as hot as, say, the East Coast of the United States. Okay, so here is my drawing of a gyre. What hemisphere is this gyre in? Is it going to be in the northern or the southern? All right, so in this case, this is a southern hemispheric gyre. It's rotating counterclockwise. And so we're moving heat south towards the South Pole, and we're moving cold northward towards the equator. All right. And so we didn't know a whole lot about our oceans, and we still don't. I mean, we had that really catastrophic event recently with the little submersible that went missing, and we talk a lot about how we don't know our oceans. Our oceans are huge. Okay, 70% of the surface area of our planet is ocean, and so sometimes we have to use creative ways to understand some of the interesting features of our ocean. And so I have this cute little video here I want to show you, which you'll see deals with accidents that have led us to understand how our oceans circulate, which is pretty cool. So we'll watch this video here about 29,000 rubber ducks.
For 99 cents. In January 1992, the Evergreen Everlaurel set sail from the United Kingdom and headed due east. It carried the normal things cargo ships carry: textiles, electronics, food, and rubber ducks. I have no idea what the animator is doing because I was of course referring to Hong Kong, United Kingdom. I'm also no fun at parties. The ducks and other bath toys were manufactured in bordering China and then brought to Hong Kong, one of the world's largest ports, to be shipped to Tacoma, Washington, and they were partially successful at this because the ducks made it to here, just south of the Alaskan Aleutian Islands, before the Everlaurel encountered a storm. In the huge waves, the massive cargo ship rolled 40 degrees to one side, and, as the old saying goes, rolling your ship 40 degrees to the side is bad, so 12 containers fell off into the icy waters below. In one of those containers were those rubber ducks, 29,000 of them. Rubber ducks are made of rubber, which is waterproof. Now, pretty much every duck in the world has a hole in the bottom, and most rubber ducks do too, except for these. It was just a choice made in manufacturing. Because of that, these ducks would never take on water like normal rubber ducks, and therefore floated forever. Wait, never mind, that's a stupid idea. About a year after that North Pacific storm, something unremarkable happened. 4 rubber ducks washed ashore in Sitka, Alaska. Then more washed ashore in Japan. Then more appeared again in Alaska. Small numbers were also found on beaches in Indonesia, Australia, New Zealand, and South America. Discoveries of the toys then slowed down after 1996. Discoveries of new continents also slowed down after 1996, but that's probably unrelated. By this time, scientists were keenly following the movements of these ducks. You see, it's fairly difficult to actually track the ocean's currents. You can drop a buoy, but a single buoy can't verify the movements of all the 26 quintillion gallons of water in the world's oceans. Scientists have created models that predict how currents flow, but it's difficult to prove their predictions. The normal method to measure current is just to release 1,000 or so bottles with messages in them, but with those, only some make it to shore, and only some of those get found, and only some of those get reported to those that release them. In the Pacific, for example, only about 2% of all drift bottles ever released are found and reported. Just to summarize then, a higher proportion of people are able to find and report a tiny glass bottle from the world's largest ocean than are able to find and follow my Twitter account. Those bottles may be salty from their float, but I'm saltier. Those ducks, however, were sweet ocean current trackers because there were just so many of them. No scientist could ethically dump 29,000 rubber ducks into the world's oceans. After all, humans already dump 8 million tons of plastic into the oceans each year. That's more than the weight of 7 football fields combined. Since this container just happened to release its cargo, however, they might as well use the data. An oceanographer named Curtis Ebsmeyer therefore started making predictions based off his ocean current model of where and when the ducks would make landfall. And then, when they did, his model was proven. One of his boldest predictions was that the ducks would make their way north, through the Arctic ice, and into the Atlantic. This would explain why the ducks stopped making landfall in significant numbers after 1996, and, as it turned out, this did indeed happen, with the first ducks in the Atlantic being retrieved in Canada in 2003, then subsequently in New England, Iceland, and UK. Now, this current data was so valuable that there was a $100 reward to anyone who found and reported the location of a duck verified from that original container. Nowadays, however, these ducks are so popular that they have been purchased for up to $1,000 at auction. From that one lost container, these ducks are now spread out all around the world, still floating across our oceans. From time to time, they still wash ashore, and if you happen to find one, you could be the world's next thousandaire. If you do find one of these ducks, I know exactly what you should do with your newfound fortune. You should invest in yourself by signing.
Okay. So, a cute story there. And this is true, right? So we were able to track the landfall of these rubber ducks, and it helped prove our theory on how our oceans circulate. Okay, and it's not just rubber ducks; it's other things like shoes and things that could float. So there's oftentimes a lot of poor weather conditions off the coast of Alaska, which just so happens to be a popular shipping route. And so oftentimes during these really strong storms, shipping containers fall off and things just start floating and go missing in the ocean. So we were able to measure our ocean circulation via these accidental experiments. Okay. And our gyres also create another phenomenon, which is more like a catastrophe, really, in that this circulation, right, makes it hard for stuff to get out of, right? It's a whirlpool and everything kind of comes into the middle. And so this convergence creates what's known as the Great Pacific Garbage Soup. Sometimes people call it the garbage patch, but you can't actually see the plastic from the surface. A lot of it's kind of floating underneath the surface, kind of buoyant. And we have huge amounts of plastic in our oceans because plastic is made to not break down. And when you make stuff that doesn't break down, it doesn't break down. Okay. And so we have this garbage soup out in our oceans. And there's this company called the Ocean Cleanup and they're on a mission to try to help clean up some of this plastic. Obviously, it's not the end all be all. Like, we have to just stop allowing plastic to get into our oceans to begin with. But it's an interesting project to try to help with that. So we'll watch this. I don't think I loaded this one, but here we go.
Plastic pollution is one of the biggest threats the oceans face today. But how much do we really know about it? On its mission to solve this problem, the Ocean Cleanup just published the most advanced research ever on the Great Pacific Garbage Patch, the largest accumulation zone of ocean plastic on the planet. Scientists have been studying this area since the 1970s, mostly by dragging a small sampling net through the ocean. The Ocean's Cleanup's researchers believe this method was valid only for small debris and covered too small an area to reliably measure larger debris. So, in the summer of 2015, the Ocean Cleanup launched the Mega Expedition, crossing the patch with 30 boats simultaneously. In addition to using many small nets, 2 giant trawls were towed behind the fleet's mothership. In total, they brought back 1.2 million plastic samples. All were hand-counted, identified, and classified by type and size. A monumental task, taking a team of lab technicians 2 years to complete. However, the largest debris appeared less frequent and more scattered. Quantifying the debris required an area 20 times larger than the Mega Expedition to be covered, something only possible from the sky. The Ocean Cleanup ran the first ever aerial surveys of a garbage patch by converting a former military aircraft into a high-tech research platform. Cutting-edge sensors allowed them to reconstruct the 3D shapes of large debris to calculate their mass. The results of all this work? The Great Pacific Garbage Patch measures 1.6 million square kilometers. That is 3 times the size of France. The patch contains 1.8 trillion pieces of plastic, which equals 250 pieces for every human in the world. The total mass amounts to 80,000 tons, 4 to 16 times more than previous estimates. 92% of this mass is made up of the larger objects, all of which are destined to fragment into dangerous microplastics over the next few decades, if left under the effect of sun and waves. And because the findings show that pollution in the patch is increasing exponentially, the plastic is unlikely to go away by itself. These results paint a new picture of the problem and provide a baseline for the cleanup of the Great Pacific Garbage Patch, set to start in 2018.
Okay, so two causes of that, right? One is human pollution of plastic into our oceans, but then also the reason it's all kind of accumulated in these areas is because of our ocean gyres. Okay, so if you want to learn more, Google Ocean Cleanup. They're doing work. I mean, it's not going to fix everything, but it's really impressive what they're able to do. Okay, so thinking about how those gyres impact our climate, right? We mentioned that certain sides of our oceans will be warmer because of those circulations. And when we look here, we can see our warm currents and our cold currents and how they form on our ocean basin. So let's look at different continents here. So let's look at Australia and South America. When we think about the circulations, we're going to see is the climate of Eastern Australia or Western South America more humid at 30 degrees. All right. All right, so when we think about this, 2 things. Humidity, we talked about water vapor on Tuesday. And we see that saturation vapor pressure or saturation mixing ratio is a function of temperature. So warmer air can have more moisture in it, which lends itself to higher humidity. And so when the ocean current is bringing more heat, hotter water, it will be more humid. Okay. And so what scenario is that happening in? Well, it's happening here in Eastern Australia. Okay. So Eastern Australia is located next to a warm ocean current. And so it will generally have higher humidity than, say, Western South America over here, because that current is cold. Okay. And so this lends itself to impacting the climate of these different regions. So when we look at this, we can actually make, I guess I didn't do this one. We can make some generalizations, okay? And when we look at the basin, an ocean basin, I just want to kind of square these off for you, draw some diagrams here. So here is a basin, right? The whole ocean, and there's a continent on each side of the basin. So when we box off our basins, and you'll just have to type your answer in because I forgot to add it to the poll. You can just type either A or B, really. At the same latitude, the blank side of the ocean basin will be warmer. Is it going to be the east side of my basin or the west side of my basin? Will be warmer. Okay. So when we look at the basin itself, we're looking at just the ocean. And so when we look at the ocean basin, which I've boxed here for you, my 5 big ocean basins, we see that on the western side of each basin, there is a warm ocean current. Okay, so at the same latitude, the western side of an ocean basin will be warmer. Now, if you're thinking about, well, what about the land? Well, you have to determine, is the land mass on the eastern or western side of the ocean basin, right? So if we look here at California, California up here in North America is technically on the eastern side of the Pacific Ocean basin. And so it's cooler. But the East Coast, like New York, Florida, the East Coast of the United States is on the western side of the Atlantic basin. So it's warmer, more humid. I can tell you that for sure. My mom is in South Carolina. That's where she lives. And she said it's been over 105 degrees and super humid every day. And I'm just like, no, thank you. Okay. That's how the gyres and our surface ocean circulation are going to impact the climate. All right, some other currents are our equatorial currents, right? Water is moving mainly with that easterly trade wind because right near the equator, the Coriolis effect is near zero, right? So you don't get as much deflection in this surface current, the surface ocean current. Rather, those currents are moving mostly east-west. And then we also have the Southern Ocean current. And because there is really no continent around, there's no land to break up the Southern Ocean, you get a pretty much continuous flow in the Southern Ocean. All right. And so the next thing we have is the deep circulation. Okay, so we talked about our surface driven by the atmosphere. Now what's happening beneath the surface is the deep circulation driven by density. Okay, so when we think about our oceans, just like our atmosphere, they're three-dimensional. So here, for example, we can see the depth of our ocean. And so the ocean, water is going to be moving down and up. And in the deeper portion of our ocean, It's driven by density. Okay, so remember, density is how much something either floats or sinks. And in our oceans, we call this deep ocean circulation driven by density the thermohaline circulation. So thermo means temperature. Haline is salt or salinity. Okay, so it's temperature and salt. And this is how 90% of our ocean water circulates. So only about 10% is that surface current. The rest of our ocean is moving slowly by this density-driven thermohaline circulation. So very, very slow. We're talking 10 to 20 kilometers per year. It moves really slowly, which is why when we talk about the storage of carbon, our oceans are storing a lot of carbon, and it takes a long time for that carbon to come back up through this deep ocean circulation. Okay? So here are some characteristics about our oceans, right? So this is a map showing our August ocean surface temperatures. Okay? Now, it's warmer in the near the equator, near the tropics, and it decreases towards the poles. Okay, obviously because of our seasonal influence, right? How much heat we get, how much insolation we're getting from the sun. And our temps range between about 0 and 30 degrees Celsius. And again, the reason why our ocean temperatures don't get much hotter is because we just don't get enough heat from the sun. And that ocean has so much capacity to hold heat. Of course, the oceans are getting a little bit warmer now with climate change, but this is kind of the range that we see. And when we think about salinity, what's in the ocean? What's in that salt? Well, most of the salt is what we think about as salt, sodium chloride. So about 55% of the dissolved material is chloride and 30% is sodium, so sodium chloride, table salt. And the rest are different ions like sulfate, magnesium, etc. Now, the way we express salinity is parts per thousand, which means that for every kilogram of seawater, the range is 33 to 37 per mil, which is 33 to 37 grams of dissolved salt per kilogram. Okay, so it's not a percent, there's an extra little zero there in that symbol, it's per thousand. So per 1,000 grams or 1 kilogram. All right, so let's practice. How much salt would be in 2 kilograms of seawater that has a salinity of 32 per mil, parts per thousand? Okie dokie. So it is grams per kilogram. So if we have 2 kilograms, let's just start with 1. 1 kilogram, that means we have 32 grams of salt. And because we have 2 kilograms, you would multiply 32 by 2 and get 64 grams. Okay, so the answer is in fact C. So it's not that much salt, but it does make a difference. Okay, so here is a map of our world oceans showing salinity. And in this case, it's PSUs. It's the same idea. It's 38 per mil, so 38 grams per 1,000 grams or per kilogram. And so you can see that we have our hot spots of salinity that align with our gyres. Okay, so there's 5 big gyres in our oceans, and those also coincide with the higher salinity regions. And that's due to the fact that these areas are prone to higher evaporation rates. If you're taking more water away, you're going to leave the salts behind. So these areas are generally a little bit saltier. Okay, but look, we're talking about 38 to 31. We're talking about a difference of 7 grams per kilogram. So not a huge difference, but it is really important for our circulations. So how do we add, or why do we get more salts or more dissolved materials in our oceans? Well, the way we get salts and dissolved material into our oceans to begin with is through processes like volcanoes, dust, mid-ocean ridges, so where we're creating new crustal material, chemical weathering, how our rocks are breaking apart. We can get rid of salt from our ocean water through biological activity. So some of these salts, these ions, are nutrients, and animals, or mainly critters like little plants, will take some of that material up. And we can also form rocks, and that can take away some of those salts. Okay, but these processes change ocean salinity on incredibly long time scales, like hundreds of thousands of years. The way we can change salinity on much shorter time frames is some of these processes. Okay, so in A, I'm showing you a really hot, sunny day where we have a lot of evaporation. B is a day where it's stormy, there's a lot of rainfall. C is the Amazon River in Brazil, putting off a lot of fresh water. We call that freshwater influx into our ocean. And then we have sea ice forming, where we're freezing ocean water. So my question for you is, which 2 panels here, A, B, C, D, show processes on short time scales that can decrease ocean salinity, lower it? All right, so it's either B and C or C and D. So we're going to talk about sea ice a lot next week. In fact, on Tuesday, we have a guest speaker, Dr. Zach Labe, who is a specialist in sea ice and in Arctic climate change. And he's going to do an amazing presentation, I'm sure, about what's happening in our Arctic. But when sea ice forms, that ocean water is evaporating, or not evaporating, geez, it's freezing. And during that freezing process, salt gets ejected. Okay, you can't freeze the salt with the water. And so D actually is going to increase our ocean salinity a lot. Okay, so sea ice forming is really important for increasing our ocean salinity. And so the answer here that is decreasing or lowering salinity is adding fresh water, water that doesn't have as much dissolved salts. So that would be rain and fresh river flow. Okay, so both A, when you evaporate water away, again, you're not going to take the salt with it. Those processes are going to eject the salt. And so A and D are going to increase salinity. Okay, so our ocean salinity variations are going to, excuse me, blah, blah. I get too excited. Our surface ocean salinity varies due to these addition and removal processes. So evaporation, precipitation, freshwater discharge, and the formation and melting of sea ice. Okay, so that sea ice formation excludes salt and it increases the ocean salinity. So let's do a few of these questions and then we'll take a break. But I want us to think about these and have it on our mind. So let's think about which of our water types will be denser? Salty water or fresh water? Okay. Yep. So salty water is more dense than fresh water because there's those salts dissolved and they have mass. And in fact, their mass is greater than that of waters. And so it will be more dense. So in a battle between salty and fresh water, the salty water will sink. What about temperature? Which is more dense? Cold water or warm water? Which will sink? All right. Right. Cold water, right? When we're thinking about our air, we always say that warm stuff rises. Same thing is true in our oceans. If you had cold and warm water in a jar or in a glass, the cold water is going to sink while the warm water rises. Now, if we mix these all together, if we have salt and temperature, which is going to be our most dense water type? All righty. Yep, it's going to be our cold and salty water. Now, we're going to pause here and take a decent break. While you're relaxing, taking a snack, think about how we can get super cold and salty water. Okay, so let's just take 20 minutes and let's meet back exactly at 3 o'clock. I'll see you at 3. All right, so how do we form salty, cold water? Well, looking at this is a map of the world showing our great ocean conveyor belt. This is that deep ocean thermohaline circulation. And these purple areas are where we create very cold, salty water, mainly through that sea ice formation process. So I mentioned that when the ocean water freezes, the salt gets ejected. And so we're creating super, super salty, cold water in these polar regions, in the Arctic and the Antarctic, where we're creating that sea ice. Okay, so sea ice, the annual freezing of our ocean waters, is really important for the thermohaline circulation. Okay, so I have a little video here of a demonstration that shows this thermohaline circulation. Oh, gotta watch this ad first. Hold on here. Here we go. So it's a quick little video, and what they're doing is they're putting some ice, right? It's gonna create a very cold water beneath, and they'll put some food coloring, some food dye in, and it helps us visualize and see how the water is moving or flowing within this this tank here. And so you can see that that cold water here is very, very cold, and it's sinking down to the bottom of the tank. Okay, imagine the tank is our ocean basin. So sinking deep down. And in the opposite sense, at the equator, we'd have warmer water. And so it creates basically like this convection system in our oceans. All right. So that is that. And I also want us to watch this, and this is going to combine some of our surface current flow with that deeper ocean current, the deeper thermohaline circulation. So let me get this plane unmuted.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them.
All right. So our thermohaline circulation, 90% of our ocean water is moving through this process, okay? So we're creating cold and salty, deep ocean water via mainly that sea ice formation process. And so when we think about the vertical structure of our ocean, we were to look from the surface down to the deep depths of our ocean, we have different profiles of things like temperature, salinity, and density. Okay, so our thermo temperature profile is on the left here, and we can see that as we go deeper, the temperature gets colder. As we look at our deep ocean, our salinity gets saltier. And as we go deep, our density also increases, right? So the more dense water is going to be located deeper in the ocean. Okay, so let's just recap what I just said here. But with increased depth, what's happening to salinity? Salinity is in the middle. Okay, so yes, as we go deeper into our oceans, down into that deep ocean, our halo profile, our salinity profile is that we get saltier, gets more, more salt, higher salinity with depth. Okay, now again, thinking of our ocean in 3 dimensions, we can look here, we have near Antarctica and near the Arctic, we have the formation of our deep waters, those deep, salty, cold waters, they form and they flow around. And there's actually multiple layers in this thermohaline circulation. It's not just surface and deep. There's mid-level waters and like higher level waters. It's actually a really complex system. And what's really important is that once that water forms, that deep water forms and it sinks down deep into the ocean, it's no longer in contact with the atmosphere. So it's no longer exchanging signals with the atmosphere. So for example, once we start taking carbon dioxide and storing it deep in our ocean, it's no longer, in touch. So that carbon stays deep in the ocean for a long time, so about 1,000 years. And that's one way our ocean, our deep ocean circulation is helping regulate our climate. And so one of the ways in which we've figured out how long water stays in the deep ocean and how long that thermohaline circulation takes is by using radiocarbon dating. Okay, so radiocarbon, or 14C, is a radioactive, naturally occurring element in our Earth system. And you might have heard of radiocarbon before, like carbon dating, how we figure out how old trees are, for example. And basically the idea here is that once the water and the carbon, the CO2 in that water is no longer talking and touching and interacting with the atmosphere, that 14C starts to decay away. And we know the rate of that decay. We know how long it would take. And so we can use it as a way to date how old things are. Okay, so this is from a research paper. You can see the different colors here of our oceans, and the colors represent the 14C age, or the carbon 14 age of the water. So based on this research, this data, where is the oldest ocean water found? Okay, so when we look at these images, right? So this is a image from a scientific peer-reviewed paper. You know, when we look at this, we want to look at all the information that we can get out of this diagram. So we're looking at longitude, latitude, the continents are shown in white. So this area over here is the Atlantic, and then everything over here is the Pacific Ocean. The color bar on the right is showing us the carbon-14 age in years. So how old is the carbon using that radioactive measurement? And we can see that the redder colors tell us that that water is older. So our oldest ocean water is in the North Pacific Ocean. Now, using the same data set, can we estimate how old the oldest water is? So looking at the data again, how old is the oldest water in our ocean? Alrighty, so again, where the oldest water is, it's in our North Pacific, and we can see that that deeper red is pushing over 1,000 years. So the answer here is D, over 1,000 years old. And so this radiocarbon measurement, this carbon dating, has allowed us to calculate and determine how long that thermohaline circulation takes. So in the video, they said about 1,000 years, and they're right. It's about 1,000, maybe even about 1,200 years. And so it takes 1,200 years. So once that water sinks, so what's happening here is the water is sinking near the Greenland area and sinking near Antarctica, and it's flowing all around, and it ends up in the North Pacific. And it takes 1,000 years or more. It's pretty remarkable. So our oceans, as I mentioned, are dissolving or absorbing a lot of atmospheric carbon dioxide. So this data series, it's called the Aloha data series. It's a station off of Hawaii where they're measuring the amount of dissolved carbon dioxide in the ocean waters through time. The red line is showing the atmospheric carbon dioxide, that Keeling curve measured on Mauna Loa on the Big Island. The green here is showing the seawater dissolved carbon dioxide. So you can see that as atmospheric carbon increases, so does dissolved ocean carbon. And the blue line is showing the seawater pH. So as we dissolve more carbon into the ocean water, the ocean pH, which is a measure of acidity, is getting lower. And if you remember on the pH scale, the lower the number, the more acidic. So the idea of ocean acidification is that we are dissolving more carbon dioxide. And when carbon dioxide reacts with water, it creates a weak acid called carbonic acid. And this is creating a more acidic ocean. To clarify, the redder areas on this graph here, on this image, are just showing you age, okay? This is not anything to do with temperature. I know it's blue and red, makes you think temperature, but in this case, in this graph, this is just showing age. Age basically since it was at the surface. Yeah, age since it was at the surface. So the darker blues here are young water. It's recently become deep water, and the red is old. It's been down in the depths for a while. Okay, so our ocean gives and takes a lot of gas and heat. This is a very big exchange process, and we're going to talk a lot about this when we talk about the carbon cycle, just an introduction. But this idea of air-sea flux, that we're moving energy, materials between the atmosphere and the ocean. And this is happening, this energy and mass exchange is happening because of the fact that we have wind and breaking waves, and all of this is churning up that surface. It's not a quiet ocean surface, it's a lot of motion. And that motion, that turbulence allows for the exchange of bubbles and gas and energy. And so we're going to talk a lot about that in a few weeks, but it's important for our climate because 70% of our Earth's surface is ocean. The oceans are a large reservoir for carbon. So this is a carbon cycle diagram. It shows you the reservoirs kind of as boxes here. We can see that our surface ocean is a reservoir. Our intermediate, middle, and deep ocean is a reservoir for carbon, and our ocean floor is a huge reservoir of carbon as well. And we're going to talk in so much depth about this type of diagram and this carbon cycle, but just to reiterate that the ocean is really important for our climate system. So now I want us to talk about how we have some interannual, meaning every few years, changes to our ocean circulation. And you've probably heard of this, especially if you've grown up in California or near the coast, or really anywhere, because it's now so common to use these terms to talk about how our climate is changing. But the El Nino Southern Oscillation, also called ENSO, is this change in our Pacific Ocean circulation. So El Nino is a little boy in Spanish, and the history of the naming of El Nino is that in the early 1600s, South American fishermen noticed these time periods where there was unusually warm water in the Pacific Ocean. Okay, and so they named this the El Nino, and the El Nino de Navidad is the warmest water conditions peaked around December. Okay, and so they named it this El Nino. So warm waters in the Pacific Ocean. So when we focus on our Pacific Ocean, remember here's some reference, North America's up here on the right, South America's on the bottom right, Australia and Asia would be over here on the left. Typically, in normal conditions, normal circulation, we have our easterly winds pushing water towards Australia. Okay, and that's those equatorial winds. Remember, they're pretty much east-west, right along the equator, because there's not a lot of Coriolis effect there. And so what's happening is we're pushing water away from the coast of South America, which creates a lot of upwelling. Okay, we're removing water from the coast, so a lot of cold water upwells and creates pretty cold temperatures there. Cold water, nutrient-rich water. On the other side of the ocean basin near Australia, that water's kind of piling up and it's much warmer because the equator's warm and we're not getting a lot of deep cold water coming up there at all. And so generally what happens is the warmer ocean water leads to more evaporation and more rainfall. So we see a lot of rainfall over Australia and the Asian continents here. Okay, so much more rainfall on the western side of the basin. Drier conditions on the eastern side of the ocean basin and much colder waters. Okay, so big thing here is there's a lot of upwelling along the South American coastline. Now, sometimes those really powerful easterly winds either weaken or entirely reverse. Now, why that happens is something we don't really understand. It's just a variability, interannual variability in our system, in our climate system. And so when those trade winds weaken, then we're not moving as much water away from the coastline of South America. And so we're not going to have any upwelling anymore. Okay, because you're not pushing water away, you're not pulling it away. And so the upwelling here is gone. Now, That means the warm waters that used to be pushed towards Australia and Asia are now hanging out along the whole equatorial Pacific Ocean. So during the warm phase of the El Nino Southern Oscillation, also called El Nino, we're stopping upwelling and we're shifting the warmer waters across the whole basin, ocean basin, and it also shifts precipitation. So now there used to be precipitation over near Australia and Asia, and now a lot of the precipitation is shifted either towards the center of the ocean basin or all the way to the eastern portion. What does this look like? Here is the 2015 year as an example. Here's what our ocean temperatures kind of look like in the equatorial Pacific in a neutral or normal phase of the El Nino Southern Oscillation, or ENSO. During an El Nino condition where we've weakened those trade winds, we've stopped the deep upwelling of cold, nutrient-rich water, then we get really warm temperatures along the equatorial Pacific. Okay, so we can see that on the right here in November of 2015, we had temperatures of 2.5 plus maybe even 5 degrees C warmer, an anomaly. That is El Nino. So when we say, oh, we're in El Nino, we mean our ocean is much warmer in the Pacific than normal. Now, the opposite can happen too, where we get extra cold conditions. That's La Nina, cool conditions. It's like the normal circulation, but stronger. So we have enhanced, stronger easterly winds in the equator, and that creates even stronger upwelling and much colder ocean temperatures and more rainfall along Australia and Asia. Okay, so we have El Nino, warm phase, La Nina, the cold phase, and then we have neutral, which is just kind of average, which means there's still cold waters. They're just not as cold. So here's some real sea surface temperature data from the 1998, 1993, and 1997 period. On the right of each figure is South America. On the left is Australia and Asia, Indonesia, Asia. And I want to know which profile, A, B, or C, is showing me a La Nina event of ENSO. And I should say the sea surface temperatures are color-coded and the temperatures are shown on the right. All right, so looking at this, La Nina is that enhanced circulation, the enhanced upwelling. And so when we're looking at this, it's meant to have colder waters along South America because of the normal conditions. So we have cold waters in B, we have some, but a little bit reduced in C. But we can see that the cold ocean takes up much more area in A. Okay, so A is actually La Nina conditions. Now, still same profiles here. Which one of these would be El Nino, where we got much warmer conditions? Alrighty, so yes, Here we go, C, right? So if you look at panel C at the bottom, we can see that the warm temperatures, blip, have extended all the way back and are like near and touching the coastline of South America, and the area of cold ocean temperatures is greatly reduced in size. Okay, so the top panel is La Nina, the middle is neutral or normal, and the bottom is El Nino. Okay, and so you can see just how much change happened. And so La Nina is just extra cold, so the cold moves to the west. El Nino is extra warm, the cold moves to the east. And currently, our current situation in the Pacific Ocean is that we're in an El Nino. Okay, so I took this a few days ago and posted it here. This is June 8th. This was the advisory. They might have posted a new one. I'll check right here. But we can see along the equatorial Pacific, our ocean temperatures are much warmer. Okay, so let's actually just check it out. What phase did they post a new one? Yeah, July 13th, more recent, and we can see we're in an El Nino advisory. The El Nino, the warm phase of the El Nino Southern Oscillation climate pattern continues. Odds are that it's going to last through the winter. It's going to be a pretty strong one, meaning the temperatures right now are 9 degrees Fahrenheit warmer than average right along the coast of South America, which is not great for some of the climate in that region, okay? So when we look at timing of El Nino and La Nina events, we have modern records, instrumental records, meaning, since we've been keeping track of the sea surface temperatures starting in like the 1980s. The red here is the warm phase of ENSO or El Nino. The blue is La Nina. Typically, either phase, the cold or warm phase of ENSO, lasts for about 12 to 18 months. They occur every 2 to 10 years. It's not a perfect oscillation in the sense that, for example, we were in La Nina for like 2 or 3 years, and then we had several El Ninos in the 1990s. Okay, typically based on our machine learning and technologies and just having more data and longer records to analyze, we are able to now predict El Nino or La Nina about a year in advance. So we were kind of anticipating we were going into El Nino about 6 to 8 months ago. We can't predict the intensity of each one of these events. And we still really are learning so much about El Nino. There's actually a lot of work at UC Irvine to understand El Nino because it has such lasting impacts on climate. So 1997, 1998, that El Nino was the most intense on recent record, followed by the 2015, 2016 El Nino. What happened during those years? Well, here is a summary graph map showing you what are some of the impacts to the climate system during El Nino. So why do these things happen? Well, remember, the ocean and the atmosphere are communicating. And so when you start to change a large portion of the ocean, make it much warmer, that's going to impact the atmosphere and that heat gets redistributed. So the El Nino event in 1997 and 1998 caused about 2,100 deaths worldwide and $33 billion, not accounting for inflation, in damage worldwide. Some of the damages are things like drought, forest fires, increase in tropical storms. The big thing here is if we look at the coast of South America, big impacts to coral reefs. Coral reefs are very sensitive to temperature. You can damage them quickly with temperatures that are 9 degrees warmer than average. Big impacts to marine life. Okay, so typically the coast of South America, the western coast of South America, like Peru, is a huge fishery ecosystem. And when those waters become so warm and we lose all the nutrients, massive disruption to that marine ecosystem. Okay, so worldwide impacts. Wildfires, big wildfires, droughts, flooding. So we said the precipitation patterns change. So places that are not used to seeing a lot of rain, see a lot of heavy rain. We get flooding, we get landslides, especially in the mountainous areas of the Andes. Impacts our Atlantic hurricane season. The idea is that heat gets redistributed. Heat is needed to fuel hurricanes. Also impacts our fisheries. Massive, massive changes to the climate. And so we're anticipating that this is going to happen this year into our winter, early spring. Okay, so what's happening with hurricanes? Well, the El Nino influence is that there's usually fewer here, right near the equator, but we get more in other places. So you can click on this and check more, check it out. We're not going to talk too much about hurricanes in this class, but it is important when we think about, some of these interannual changes in our climate. And you do not have to know all of these, but these are some maps from climate.gov, which is based out of the National Oceanic and Atmospheric Administration, kind of demonstrating some of the big picture trends or changes that we see to the climate during El Nino. Okay, so El Nino patterns over winter, December, February, Northern Hemispheric winter, we see obviously the equatorial Pacific is warm and wet. In the United States, we see quite a bit of wet and coolness, and we also see pretty warm conditions in Canada and Alaska. In Indonesia, it's very warm and dry. That's usually leading to forest fires. In Africa, also warm and dry usually increases forest fire, wildfire activity. In terms of the same El Nino change, it's also going to have impacts in the summer season or summer months, June through August climate, which is winter for Southern Hemisphere, you can see. So it's big. And so again, we're still trying to understand and research what all happens. Okay. We're thinking just locally on the US, here are the generalized changes. So with El Nino, when we're going into winter now, what's going to happen is our jet stream moves south. Okay, and we talked about our jet stream, those really strong upper level winds, it moves south, which means our storms, the wintertime storms get pulled south and impact more southern states. Okay, what are other things that can happen? So there's been some research to look at how El Nino on the left and La Nina on the right impacts tornadoes and hailstorms. Again, these extreme weather events. So that's pretty cool. Again, we're not going to go into detail here, but we could definitely see some changes, whether it's less storms or more storms, there's observable changes. Now, what about global temperature? Well, ENSO is increasing, or El Nino, excuse me, we're thinking solely about the warm phase here. El Nino makes that huge ocean of the Pacific much warmer. And so when we look at the global temperature anomaly, color-coded by the phase of ENSO. So red is El Nino phase, gray is the neutral or normal phase, and blue is La Nina phase. We can see that some of the warmest years on record coincide with El Nino. Okay, so this was 2018, 2019 was a strong El Nino. And 2022, 2020, or 2023, 2024 is very likely to be the next warmest year because very strong ENSO. Now, as I mentioned, huge impacts on fisheries. Why is that? Well, fish have to have a certain habitat, right? They have a niche environment that they can sustain. And so when the waters are much warmer at the surface, those fish move deeper to stay in that temperature that's better suited for their metabolisms and their way of life. And so when we had fisheries, these boats up here trying to catch some fish, they could do that no problem. But now the fish are too deep and we cannot catch them. Okay, so that's one of the main impacts on fisheries during El Nino. Some current news. I don't know if you've been paying much attention, but the world is facing a heat wave. And I don't mean that jokingly. I mean seriously, in the sense that our oceans are so warm right now, even when we take all of them together. not just the equatorial Pacific, all of the world's oceans. So when you combine all of the world's oceans, this is what's happening right now. This is black line, shows you the temperature. We see that it is the hottest our oceans have ever been since we've been taking data. So absolutely unbelievable, super warm temperatures, right? We call these marine heat waves, just like we can have heat waves on land, we have heat waves in the ocean. So again, here, this is the ENSO, El Nino situation, but we also see very warm ocean waters in the North Pacific, off the coast of Florida, off the coast of Africa, quite intense marine heat wave going on right now. Okay, so the ocean is heating up. Okay, so this again is showing you this graphic of how much ocean heat content change. So the oceans have absorbed about 90% of the total warming due to climate change or global warming. So when you think about, starting 200 years ago when we started pumping carbon into the atmosphere by using and burning fossil fuels, the extra heat that's been trapped by that increase in greenhouse gases, 90% of it is in our oceans. Okay, so the oceans are doing a lot of work right now. And without our oceans, our atmosphere would be much warmer. Okay, so the oceans are heating up, and we're going to talk really about some of those consequences in a few weeks when we think about what will happen if our oceans continue increasing in temperature. Okay, so our sea level is rising as well, partly due to the fact that the oceans are getting warmer and they're expanding in volume. And we also have a lot of land ice, our glaciers melting, adding water to the oceans. Okay, so that is all I have for you today. I would like to remind you that homework 1's new due date is tonight. So I hope you had a chance to get everything squared away, a little less chaos in our brains. So that's due tonight. Today's check-in, please get that in. There's one aspect of the check-in where you can think about some questions you might want to ask our guest speaker on Tuesday about the Arctic and climate change. And I link you to his website so you can see a little bit about what his research is. Quiz 2 is due Monday, I think. And if you haven't yet submitted your climate change solutions you'd like to do research on, please get that in. Okay, there's already been a lot of you that have done so, so the list is dwindling and what's available for the research. So please check that out. It's all linked on my Canvas, excuse me. And my last comment is that because we've pushed homework 1's due date, I've now pushed homework 2 and homework 3 and homework 4. They're all going to be due a little later, so you still get about a week worth of time on each of those. Okay. That's all I have, I think. If I forgot anything, I will send an announcement and post to Discord. Otherwise, I hope you all have a great weekend, and I'll see you on Tuesday.